Hello, my dear students. Welcome to IK Sir Chemistry classes. In this video, we will discuss nucleophilic attack on coordinated alkene. First of all, we will see what is nucleophile. Nucleophile means nucleus loving. The species having an affinity for the nucleus, that is for the positive center, is called a nucleophile. It is an electron rich species. Any molecular or ionic species having an affinity for the nucleus, that is for the positive center, is called a nucleophile, and it is an electron rich species. The nucleophile is denoted by Nu electron pair negative charge, or simply Nu containing electron pair. The nucleophile is either negatively charged or neutral species. Either negatively charged or a neutral species containing a pair of electrons, which is present in high energy molecular orbital and can be donated easily to electrophile. Please note it again that nucleophile is either negatively charged or a neutral species containing an electron pair in high energy molecular orbital, which can be donated easily to electrophile, that is positive center. Examples of nucleophiles are given below. This is positive center. If Cl- ion containing 4 electron pairs approaches this positive center, it attacks on it. H2O molecule is neutral, which contains 2 electron pairs on oxygen atom. It can also attack on positive center through its oxygen atom, which is partially negatively charged. The hydroxide ion contains 3 lone pairs of electrons on oxygen atom and also negative charge. It can also attack on the positive center. Thus, all these 3 species are nucleophiles. Reluctance of free alkene molecule towards nucleophilic attack. Free alkene molecule contains pi electron cloud above and below the molecular plane. Free alkene molecule contains pi electron cloud above and below the molecular plane. It is generally not attacked by the nucleophile because the nucleophile is repelled by the pi electron cloud of alkene. Therefore, the free alkene molecule is reluctant, is not willing towards attack by nucleophile. Diagrammatic representation of reluctance of free alkene molecule towards nucleophilic attack. This is free ethylene molecule. It contains pi electron cloud on both the sides of the molecular plane. If a nucleophile containing electron pair and negative charge approaches free ethylene molecule, an electrostatic repulsion takes place between the pi electron cloud and negative charge of the nucleophile. As a result, the nucleophile does not become able to attack on free alkene molecule and it is repelled away. It means free alkene molecule is not attacked by nucleophile. Nucleophilic attack on coordinated alkene molecule. When an alkene molecule is coordinated to metal atom in a metal olefin complex, it should be A. When an alkene molecule is coordinated to metal atom in a metal olefin complex, the formation of olefin to metal sigma bond involves the transfer of pi electron cloud of alkene to the vacant hybrid orbital of metal. In metal olefin complex, olefin to metal sigma bond is formed, which involves the transfer of pi electron cloud from alkene molecule to vacant hybrid orbital of metal. As a result, the coordinated alkene molecule becomes electron deficient due to the formation of this olefin to metal sigma bond, and the electron deficient coordinated alkene molecule can be readily attacked by nucleophiles. Wacker process. The reactivity of coordinated alkene towards nucleophilic attack constitutes the basis of Wacker process. The Wacker process is based on the reactivity of coordinated alkene molecule towards nucleophilic attack. And this Wacker process involves the aerial oxidation of alkene to carbonyl compounds in the presence of PdCl2 and CuCl2 in dilute HCl. In Wacker process, alkene is transformed into carbonyl compound by or in the presence of PdCl2 and CuCl2 in dilute HCl. Here, ethylene, that is ethene, reacts with oxygen of air in the presence of PdCl2, CuCl2 in dilute HCl at 120 degrees centigrade and 4 atm pressure, forming acetaldehyde. Please note that this reaction leads to decrease in Gibbs energy of the system. Delta Rg naught, a standard change in Gibbs energy of the reaction, is minus 197 kilojoule per mole. And if any chemical reaction involves decrease in Gibbs energy, it is thermodynamically favorable, and therefore the aerial oxidation of alkene into carbonyl compound in the presence of these catalysts is a thermodynamically favorable process. The Wacker process consists mainly of following three steps. In the first step, oxidative hydrolysis of ethene to acetaldehyde takes place, and this process is promoted by PdCl2. Alkene, here ethylene, undergoes oxidative hydrolysis promoted by PdCl2. In this reaction, palladium is reduced from +2 oxidation state to 0 oxidation state, while ethylene is oxidized to acetaldehyde. In the next step, palladium, the product here in the first step, is oxidized to PdCl2, and this oxidation takes place by CuCl2, cupric chloride. PD is oxidized by cupric chloride to PdCl2, and CuCl2 is itself reduced to cuprous chloride. And in the third step, CuCl is oxidized to CuCl2 by passing air. Cuprous chloride reacts with HCl, which is present in the reaction medium. In the presence of O2 of air, forming CuCl2 plus H2O. On adding these three steps, the overall reaction becomes as follows. Ethylene reacts with O2 in dilute HCl in the presence of PdCl2 and CuCl2, forming acetaldehyde. The overall reaction is very simple, and these two species act as catalyst because they take part in chemical reaction and reproduced at the end of catalytic cycle. Mechanism. The Wacker process proceeds through following steps. First of all, PdCl2, the catalyst, combines with Cl- ions present in the reaction medium, forming 16 electron square planar complex PdCl4 2-. PdCl2 is used as catalyst in the Wacker process. It combines with Cl- ions of PdCl2, CuCl2 and HCl, which are present in the reaction medium, and thus a 16 electron square planar complex is formed. PdCl2 reacts with chloride ions present in the reaction medium, forming PdCl4 2-. This has a square planar geometry and its electron count is given here. There are 10 valence electrons in palladium atom and 2 electrons are lost because its oxidation state is +2. And each of the 4 Cl- ions contributes 2 electrons towards the electron count, and accordingly the electron count will be 16. It is coordinatively and electronically unsaturated. In the second step, one of the Cl- ions of PdCl4 2- ion is substituted by ethylene molecule, forming PD dihapto C2H4 Cl3- ion. This is PdCl4 2- ion, the square planar 16 electron complex formed in the first step. Ethylene is a stronger ligand than chloride ion, and therefore one of the Cl- ion of this complex compound is replaced by ethylene molecule. This Cl- ion comes out from the coordination sphere and its position is occupied by ethylene molecule. Ethylene molecule is coordinated to palladium 2+ ion. Please note that this square planar complex is similar to the anion of gaseous salt. The only difference is that the platinum 2+ ion of gaseous salt has been replaced by Pd2+ ion. In here it should be, this is the anion of gaseous salt. You may note that the Cl- ion trans to ethylene ligand is loosely bonded. This distance is 234 picometer, but these distances are 230 picometer. This Cl minus ion is bonded loosely to platinum 2 plus ion, and the same situation is in the case of present complex ion. The Cl minus ligand of this complex ion situated trans to ethylene is loosely bound, and hence it is replaced easily by H2O molecule, forming neutral complex. This Cl minus ion is loosely bound as in the case of anion of gaseous salt, and it is easily replaced. This Cl minus ion comes out from the coordination sphere and its position is taken by H2O molecule, and thus a neutral complex is formed, PD dihapto C2H4 Cl2 H2O. There is no charge on it. The crucial step in the Wacker process is the nucleophilic attack by free H2O molecule on the coordinated ethylene molecule of this neutral complex, forming an anionic complex containing beta hydroxy group sigma bonded to palladium atom. This is the main step in the Wacker process. It involves the nucleophilic attack by free H2O molecule present in the reaction medium on the coordinated ethylene molecule of this neutral complex, which has been formed in the third step, forming an anionic complex, and this anionic complex contains beta hydroxy group sigma bonded to palladium atom. It can be seen here. This is the neutral complex formed in the third step. Its coordinated ethylene molecule undergoes nucleophilic attack by H2O, and the result is the formation of a beta hydroxy group. This is beta hydroxy group, alpha beta, and it is attached to palladium atom through sigma bond. It is a sigma bond. Let us see the nucleophilic attack on coordinated ethylene molecule. Oxygen atom attacks on this carbon atom. This pi bond transforms into palladium carbon sigma bond, and this H plus ion comes out. As a result, OH minus, OH group becomes attached to this carbon atom. OH group becomes attached to CH2 group, and this CH2 group becomes sigma bonded to palladium atom. Thus we get a beta hydroxy alkyl group sigma bonded to palladium atom. This is the main crucial step in the Wacker process. The loss of two Cl minus ions from PdCl4 2 minus during its conversion to this neutral complex. In the first step, this complex compound was formed which has two negative charge, but during its transformation to PD dihapto C2H4 Cl2 H2O removes the anionic charge. It contains two negative charge, but it has no negative charge from the metal, which facilitates the nucleophilic attack by H2O. Since this species has no charge, it has zero charge, the nucleophilic attack by H2O molecule is facilitated during the fourth step of the reaction. If there were two negative charge on this complex compound, H2O molecule would not be able to attack on it due to electrostatic repulsion. The final and the rate determining step of the reaction involves beta hydride elimination reaction with loss of vinyl alcohol molecule, which tautomerizes immediately to acetaldehyde, which is nothing but the desired product of the reaction. In the final and rate determining step of Wacker process, beta hydride elimination reaction takes place, which involves the loss of vinyl alcohol molecule, and vinyl alcohol molecule tautomerizes immediately to acetaldehyde, and thus we get the desired product. This is beta hydroxy alkyl group bonded to palladium atom by sigma bond. This CH bond, this hydrogen atom of beta carbon atom is transferred to palladium atom along with the electron pair. It means beta hydride elimination reaction takes place. Hydride ion from the beta carbon atom is transferred to palladium atom. This is a slow and rate determining step of the process. This electron pair, sigma electron pair, is transferred here. As a result, double bond will be created here. We get vinyl alcohol molecule which comes out from the coordination sphere, and this hydrogen atom becomes sigma bonded with palladium atom. Thus we get metal hydrido complex. This beta hydrogen atom is transferred from beta hydroxy alkyl group to palladium atom, forming metal hydrido complex and vinyl alcohol. Vinyl alcohol tautomerizes to acetaldehyde as indicated by the arrow for electron transfer, and this metal hydrido complex decomposes forming palladium, H2O, HCl and Cl minus ion. It comes out as H plus ion and it comes out as Cl minus ion, both combined together forming HCl. This comes out as Cl minus ion, and palladium atom becomes free because H2O molecule also comes out from the coordination sphere. This is the final slow and rate determining step which involves beta hydride elimination reaction. If the alkene is unsymmetrical, the nucleophilic attack by H2O is regioselective. For more substituted carbon atom of carbon-carbon double bond, so that the bulky PdCl2 H2O unit goes to that carbon atom of carbon-carbon double bond which is asterically least hindered. If in the Wacker process the alkene is unsymmetrical, the H2O molecule, that is the nucleophile, attacks on that carbon atom of carbon-carbon double bond which is asterically more hindered, more substituted, so that this bulky unit goes to that carbon atom of carbon-carbon double bond which is asterically least hindered as illustrated below. Here propene molecule is coordinated to palladium, and during nucleophilic attack H2O attacks on this carbon atom of carbon-carbon double bond which is more substituted, which is asterically more hindered, so that This bulky group, PdCl2H2O group, gets attached to that carbon atom of carbon-carbon double bond, which is asterically least hindered. H2O attacks on more substituted carbon atom of carbon-carbon double bond of alkene coordinated to metal, so that this bulky group PdCl2H2O goes to that carbon atom of carbon-carbon double bond, which is asterically least hindered. And the product here is acetone. It means if propene is used as reactant in Baker process instead of ethylene, acetone is formed instead of acetaldehyde. And this reaction is regioselective. The chemical reaction in which one of the various possible structural isomers of the product is formed predominantly or exclusively is called a regioselective reaction. Thank you for watching the video with concentration. Please like and share it. If you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.